So we move on with Markov chain applications as we gradually come to the end, talking about Markov chains. Of course, that doesn't mean that stochastic processes are ending, but we've been talking a lot about Markov chains, I think, in the last couple of videos. And here we'll be looking at Markov chain applications. Markov chain applications. All right, so here, this lesson covers Markov chain application areas like Google PageRank, which is very popular in our surfing the net, genetics, like we're talking about population models, queuing systems, and we include the theory of Markov chain applications, the mathematical formulation, worked examples, and Python simulations. So we start first of all with a refresher. We've been talking about Markov chains a lot. So we've gone through a whole lot of things. So we try to remind ourselves that a Markov chain satisfies the fact that the probability of xn plus 1 equals j, given xn equals 1, xn equals minus 1, all the way down, is just simply the same thing as probability of xn plus 1 equals j, given xn equals 1, meaning that this current state determines the next state, and every state before this current state is forgotten in a Markov system. That means that the Markov property is that of memorylessness. Like only this state determines the next. Every state before now is forgotten, is not retained in the memory of the system. And then we talk about the idea of transition matrices, where we have each row summing up to 1, and each probability, of course, being non-negative for obvious reasons. And then PIJ is probability of moving from state I to state J, basically. So PII, P11 is the probability of moving from state 1 to state 1. P21 is probability of moving from state 2 to state 1, and so on and so forth. And then we talk about state evolution. We've seen all of this a whole lot. So it's talking about the state evolution. If pi n is the distribution at step n, then we say that pi n plus 1 is the same thing as pi n multiplied by the transition matrix P. Then we talk about stationary distribution. So that's the distribution pi which satisfies that pi is equal to pi p. So this represents long run equilibrium. So this tells you, so for every Markov chain, the system settles somewhere at the end of the day. So all states will converge towards that state at the end of the day, and that is what the stationary distribution is. So we've seen a couple of videos where I actually took care of that idea. So let's talk about application of Markov chain in Google PageRank. All right. So the idea is that web pages are seen as states, right? Then links are seen as transitions, and a random software clicks links randomly, right? Like you get on the internet. So every web page is a state, but every link to get to that page is actually a transition. So the model is this: the stationary distribution ends up satisfying the fact that pi is pi p, which we've seen a lot of times. And then we talk about the idea of damping or teleportation. So if you want to avoid dead ends, that ends up being p prime equals alpha p plus 1 minus alpha 1 over n, like that. So to avoid dead ends, we have p prime to be this. So where alpha now is 0.85 and n is the number of pages, right? So, and then the interpretation of that is that pi I is equal to importance of page I. So whatever the value of pi I ends up being tells us how important page I is. So we have a PageRank example here. Consider 3 pages, right? You have 3 pages, A, B, and C. So from A, you can go to B and C, and from B, you can only go to C. From C, you can only go to A. So to write the transition matrix, right, you have this. So from A, you can go to B and C. So you can't go from A to A like this. So from A, you go to, uh, B and C. And then from B, you can go to C. So this is state B. So from B here, you can go to C. That's one, because that's the only state you go to. Because from A, you can go to 2 states. So the probabilities have to be shared equally like that. Then from C, you can go to A. So that is state C. So CA, this is 1 right here. That's how you write the transition matrix based on where you can go from one state to another. So, and then we have a Python code to demonstrate that reality. So we have our transition matrix right here. And at the end of the day, we want to get the distribution, we want to get the pi. So how important are those 3 pages, right? So, at the end of the day, page A, state A is 0.38. State B is 0.21. State C is 0.39, right? That means that state C is the most important page, and state A is the second most important and the state C is the third most important. So to interpret this result, then we see that um, the page rank values that we have here now represent the long-term probabilities of a random sofa being on each page. In this specific example with pages A, B, and C, we see that page A, which the first value is approximately 0.38. This is the page rank for page A. Page B, approximately 0.15. This is the page rank for page B. And page C, third value is approximately 0.397. This is the page rank for page C. So from these results, we see that page C has the highest page rank, indicating it's considered the most important or frequently visited page by the random software model, followed closely by page A and page B. So the values, at the end of the day, the stationary distribution tells us how important each of the websites, each of the sites or states can be. Then we talk, so having looked at the application of Markov chains in page ranks, we can also look at it in terms of genetics, looking at a mutation model. So we model allele changes across generations. So you have allele changes across generations like this. So you have the transition matrix. So you have state A up here and you have state small a down here. So probability of moving from big A to small a is 1 minus u, right? Okay, the mutation from big A to small a, we see that as u, all right? So this is like small a, this is big A. Then probability V now is probability is mutation from A to V. So that's from small a to big. So it's like you have A, and then uh big A, small a like that. So we have that. So the genetics example here, imagine if U is 0.01 and V is 0.02, then we have the transition probability of 0.99 because of 1 minus U now is 0.99, U itself is 0.01, then V is 0.02 and 1 minus V is 0.98. So with that in place, then if we find the stationary distribution, that is something like V over U plus V, comma U over V, U plus V. And then if we do the if we do the Python code iteration to get the stationary distribution, we see that at the end of the day, we have 0.67, or if you like 0.68 again, 0.32. So that tells us that the first state is more important, right? The first state is more important than the second state. Or there's every chance of mutating, to states. So U now, so 1 minus U is mutation from state. So this is U right here. So it means that there's likely mutation from A to big A to small a than small a to big A based on the results we have here. And then we can also apply this Markov chain to queuing systems, MM1. Along the line in this playlist of stochastic process, we are going to look at queuing systems. This is queuing system where you have just one person servicing everybody on the queue. You can also have MMK where you have more than one person servicing people on the queue. So here now the states are the number of customers, and we have parameters like the arrival rate, mu is the service rate, and then we have the stability condition rule, which is lambda over u. So the system is only stable if the arrival rate is if a row is less than one. That means the arrival rate is smaller than the service rate. So that means that people don't take too much time on the queue. So the steady state distribution for this is given as pi n, which is 1 minus p multiplied by 1 minus rho multiplied by rho raised to power n. And of course, if we set it up that the arrival rate is 0.4 and the service rate is 0.6. So we can have that the average queue length is 0.2, 0.72742, like that. So if you just work all of this out, we have the average queue length to be this. Okay, this is such a short video because we're just talking about applications. So in summary, we see that for PageRank, right? If you apply Markov chain in PageRank, the states are like web pages, and the meaning is that we have links, and then the output talks about the importance of the page. In genetics, the states are the alleles. The what is really happening is the mutation, right? And then the output is equilibrium. So which kind of genes, what kind of mutation is more important? Is it from big A to small a or from small a to big A? Then you have queuing also as a Markov as an area of application of Markov chain. So the states are the customers, and the meaning is the service system, and the output is the queue length. At the end of the day, you want to make sure the queue length is manageable, and then nobody spends too much time on the queue, or is it in the queue? So key idea now, all applications rely on this. This gives the long run behavior of the system. That's why pi p equals pi is very important at the end of the day. It tells you the state to which the system around which the system stabilizes in the long run. So we have practice problems here. First of all, we have some fundamentals. So given the transition matrix, okay, I guess I can show them in twos. Given the transition matrix, P is this. Find the stationary distribution pi. We've done that a lot of times. That's pi. P equals pi, right? Then two, verify the following distribution. Verify whether the following distribution is stationary. That is pi 0.4, 0.6 for the matrix P. Is it stationary? That means that does the system keep... Okay, I mean, if it is stationary, right? If you multiply the two, we should get pi back, right? So I think that's a nice question to consider. So 0.4, 0.6, 0.5, 0.2. To verify, to verify if pi equals 0.4, 0.6 is stationary for p equals I want to be sure of that p now. 0.4, 0.6, 0.5, 0.2, right? 0.5, 0.2. 0.5, 0.2. That means this is 0.5 and this is 0.8. So that's all we want to do. To verify that, what should you be looking out for? So the, okay, so we say pi is stationary. Pi is stationary if pi p is equal to pi. That's what we are looking for. So in that case now, we then go ahead and say we look for pi p. So pi p is equal to 0.4, 0.6 multiplied by p. So pi is 0.4, 0.6. That's 0.5, 0.2. This is 0.5, and this is 0.8. So because we have only one row here, so we write each column here once each. So that means that pi p is equal to 0.5, 0.2. Okay, just this. 0.5, 0.2. Then we have 0.5, 0.8. So we put this over it now. 0.4, 0.6, 0.4, 0.6. So that means that pi p, so pi p is equal to this 0.5 times 0.4. That's 5 times 4 is 20. So two decimal places, that's 0.2. Okay, I wonder why I keep doing this. 0.2 plus 0.12. That's 2 times 6, 12, two decimal places. Then again, 0.2 plus 0.48, I believe. 8 plus 8 times 6, 48. So two decimal places. So pi p now is equal to, when you add these two together, you have 0.32, and you have this, that is 0.68. Well, this is not equal to pi because pi is 0.4 and 0.6. So pi is 0.4 and 0.6. So here we say that uh, since since pi p is not equal to pi, let's do it this way. Since pi p, which is equal to 0.32, 0.68, is not equal to pi, which is pi is 0.4, 0.6, 0.4, 0.6. Then pi equals 0.4, 0.4, 0.6 is not stationary. It's not stationary. Okay, so that's what we have right there. So yeah, we can try other questions. So yeah, pi 1, pi 2, all that. Explain what it means for a Markov chain to be reducible and aperiodic. Show that the rows of a transition matrix must sum to 1, of course. Construct the transition matrix for a network. A goes to B, B goes to C, C goes to AB. Okay, so A only goes to B, right? So that means A goes to Okay, maybe I want to try do this. Um, okay, I guess I want to snip. Let's go here. So I have this. I want to construct a transition matrix that follows this. So here now, so I just come and paste. So we want to construct the transition matrix. So this is P, which is equal to, so you can say A, B, C. Then you have A, B, C, like this. So you can go from A to B alone. So A to B alone, that is A to B, that is 1 here. So automatically this will be 0, 0. Then B to C, this is 1 and this is 0, 0. Then from C, you can go to A and B. So it means you can go here, you can go here, and this is 0. So these two, if you imagine they share the probabilities equally. That's 0.5 and 0.5. So this is the transition matrix for this network now. So and by getting by solving for by by solving for pi in pi p equals pi, okay, you get you get the most you get you get the order of importance, the order of importance of the states or the webs of the sites. So we've done what pi p equals p a lot of times, so you want to check that out. For tip 3 by 3, it becomes a bit more tasking, right? Apply damping factor A to this. Yeah, so please just try all of these out and see how helpful it is. So again, let me try to flash the questions one after the other. So here you have like 1 to 3, 1 to 3, then you have 4 to 7. You can say 4 to 7 here, then 8 to 12, maybe. Yeah, this is 8 to 12, and then 13 to 16 here. You have 17 to 20. Well, we can see it can still see 16 to 20. So talking about queuing, but we're still going to talk about queuing systems a lot. So this one says compute P and check the stability. Of course, P here is lambda over 2. That's 2 over 3. So 2 over 3 means you have the arrival is less than the service. That means the system is stable. So there's no trouble on the queue. So thank you so much for listening to this. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, why not go ahead, click on subscribe and hit the notification bell so you can always get alerted each time a new video is released. You can click on join also to become a member of this channel. That gives you some special privileges, right? Like getting to see some videos first or seeing some videos exclusively as a member of the channel. You can request for PDF copies of my notes. You can also hang out with me online or physically if we are in the same geographical zone at any point in time to talk about whatever interests you on this channel, be it mathematics, data analysis, data science, machine learning, scholarships, or whatever else fascinates you about this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.